Okay, so in this part, we're actually going to be exploring graphing parabolas. Now, the ministry content, it wants you to do all this stuff with equations and like subbing in and very tedious steps. But there's something called a step pattern, which will actually be a lot easier, I think, for everyone. And of course, you have access to online materials, so it just makes more sense to kind of lighten your workload. So, what I'm going to do is walk through the base function of y equals x squared, and then we will also try it with one transform function. This will just come in handy, I mean, if you're ever graphing. Having said that, there will be a couple of questions like this on the summative, but not today on the quiz. So if you want to review this at the end of the module, which will be later on this week, you're welcome to take a peek back, obviously, at the YouTube videos and just make sure that you're better understanding it. So our base function, hopefully everyone knows by now, is y equals x squared. We already kind of know what this just kind of looks like. We've explored it in the previous video and in previous days. We understand that the vertex is at 0, 0. Okay, we're going to try one with a transformed function as well, where we have to figure out that vertex point a little bit easier. A little bit more difficult, but we do understand the base function. Vertex is at 0, 0. There is something called a step pattern, which is like the basic kind of steps that are taken in order to graph this. If you've taken this course before, or if you have experience with parabolas, you might remember that we always work in steps of 1, 3, and 5. So our base function follows that order. What the step pattern tells you is how much you are moving up or down by along the y-axis as you move over by 1 unit on either side. This is going to save you a lot of headaches and a lot of equation work. So I'm going to show you what this looks like. Step number 1, when you're graphing parabolas, you are going to set your vertex and orient your graph. Your vertex is your turning point. It's your middleman. It is the axis of symmetry. So we know that this graph is going to look symmetrical on both sides. Your step pattern is 1, 3, 5. So what you're going to do is go over by 1 unit on both sides. So just like I'm doing here. And you're going to go up by 1 unit. So your step is actually the vertical movement. You're always moving over by x equals 1 unit, but your step pattern again tells you how much you're going to move up or down by along the y's. You never, ever, ever plot a point until you've done both an x movement and a y, otherwise described as a left or right movement followed by an up or down. Our first 2 points should be right here. Okay, we've taken care of the step of 1, and we're going to make sure to do it on both sides. The next step is 3. So you're going to start from that point that you just ended off at. You're going to go over by 1 unit, and you're going to go up by 3 units on both sides. Okay. Again, just notice how it's kind of like a mini staircase. You can think of it that way. The parabola will tie in at the very end. We moved over by 1 unit, and we went up by 3 units. Last step is our step of 5. So exact same thing. We're going to go over by 1, and we're going to go up by 1, 2, 3, 4, 5. Same thing. I'm going to go over and up. And I'm just going to double check because sometimes I miss a grid line or two. So 1, 2, 3, 4, 5. That looks good. You could probably predict what your next value would be. By definition, as long as you have like 3 to 5 points, you have a parabola. We actually just graphed 7. But you can probably see 1, 3, 5. What comes after that? 7, 9, 11, 13. This is because your second differences are the same. Okay, so we went from 1 to 3 to 5. Our second differences are describing the pattern that's happening in between. So adding by 2 each time. This is what makes it a proper parabola. Your last step, you're going to take all those points, draw a nice smooth curve through them, and you could also attach arrows at the end just to show the end behavior. Okay, and this should really just resemble your basic function. Okay, so I'm going to highlight it in a different color so that you can see the difference between the two functions. If you were to go back on Desmos and graph it, you're going to notice the same points. You have a vertex at 0, 0. You have your next points at 1, 1, negative 1, 1. You also have another point at 2 and 4. Okay, negative 2 and 4. So you're just basically grabbing points. Where this saves you time and energy is you're not having to constantly sub in values, and you also better capture the vertex, which is the glue to any parabola. So we're going to try one on the same exact grid, except this time we're going to have a transform function so that we can see the difference. Now we're going to write a new function right beside, so we'll have 2. Let's do maybe x minus 3, and then plus 1. Kind of similar values as the last video. I'm going to use a different color just to distinguish the difference. So I'm going to use a nice purple here. Okay, so a couple of things. Number one is we need our vertex. So that is going to be the trickiest part, is to get set up. What you're going to do here is you're going to need to investigate both the bracket with the x minus 3 and the plus 1. This right here, the plus 1, is your y coordinate of your vertex. Okay, it's true to what it actually should be. Right away, that's your y coordinate of your vertex. Where it gets tricky is within the bracket tells you your x coordinate, x minus 3. All you need to do is flip the sign, or think, how can I zero out this bracket? Because when you zero out that bracket, you're going to be left with just the y coordinate of your vertex, which is 1. For example, sine x equals 3 into here, 3 minus 3 equals 0. 0 squared is still 0. 2 times 0 is still 0. Plus 1 just gives you plus 1. So you're going to flip the sign on your bracket. And x equals 3 is your coordinate for your vertex. If it was, let's say, x plus 4, then negative 4 is your x coordinate on your vertex. So again, I'm just going to rewrite out my vertex in simpler form. You won't have to do a ton of graphing anyways, and I can also post extra resources. Even understanding a few of these concepts are great. So your vertex is at 3, 1. Okay? So it's up to you if you want to kind of go through everything, or if you want to just start with your vertex. So I'm going to start just by plotting it, just so I get a general sense of what the graph is doing. So our vertex is at 3, 1. That means it is over here, 1, 2, 3. Right here is 3 units. And we go up by 1. So this is our vertex right here for the purple highlighted function. Once you have your vertex set up, you're almost done. You just need to use your step pattern. Step pattern is usually 1, 3, 5. You're going to take those numbers and multiply by whatever your a value is. Okay, so your first thing is sign it up, grabbing your a value. Your a value is always this coordinate in front of your function. So it's going to be the value of 2. If I take 1, 3, 5, if I multiply them all by 2, I get 2, 6, 10. Let's say the a value is 3. You're then going to go ahead and triple it. What we urge you is this: only use the grid that is in front of you. So you shouldn't need to go outside of the grid at all. You're just going to fill in the values that will be settled right there for you to see. So I'll show you what we mean in a second. So the steps that you're actually using are after you multiply by whatever's in front of the bracket. So 2, 3, 4. It probably wouldn't be bigger than 4 because that graph would be way outside of the grid. So our steps are 2, 6, and 10. We're going to do the same process. So we go outside or over by 1. We go up by 2. Okay. And you know what? I'm just going to delete some of these little staircase points just so you can see a little bit better. Hopefully you have that down, or you've just taken note of it somewhere. Okay, just so you can see the difference between the graphs. I'm going to go on the other side and also go up by 2. I then plot my first points. Okay, so instead of going over by 1, up by 1, I'm going over by 1, up by 2. That is my vertical step. My next step is to go over by 1, up by 6. So I go over, I go up 1, 2, 3, 4, 5, 6. Okay, and then I plot my point. I don't really need to count on the other side as long as I've done the math well on the 1 because they're symmetrical. So I usually just kind of play a game of matching. I go back because I always tend to miss points or make a small mistake. So 1, 2, 3, 4, 5, 6. My step looks good. And I'm just going to write that down. Okay, now our next step is 10. If we try to do that, we're basically moving upwards by 10 units. I'm going to be way out of no man's land, off the grid. So I'm going to stop here and only use what's contained in front of me. Okay, as long as you have 3 to 5 points, you technically do have a parabola. So it's just kind of like a linear function. If it goes outside the grid, you already have a bunch of points set up. You can see the general shape. So I'm just going to, again, connect it with a smooth curve. Whoops. And of course, it's not working. There we go. Okay, get it as accurate as I possibly can. And then I'm just going to highlight it with that same purple color so that I can see the difference. Okay, I can also stick arrows just to show the end behavior, so both graphs are definitely going upwards. Okay, so what happened to that vertex? Well, just kind of like the transformations video previously, you went over by 3 units to the right, you went up by 1 unit. So that matches the fact that our vertex is 3, 1. We can also see that it's going upwards at a much steadier rate, okay? Or in other words, it's accelerating. So those are good descriptors when you are trying to describe the transformations applied to the graph. Okay, we won't do a whole lot of negatives just for time's sake, but this is just a good worked example of the transformations of graphs.